Hey guys, Conqueror this side, and welcome to Conqueror YouTube channel. By end of this session, you are going to get some conclusions about the boundaries. Okay, because Thevenin's theorem also actually this equivalent circuit definition from here it will be extended till Thevenin's theorem also. Okay, normally Thevenin's theorem, what people say, any complex circuit can be converted into equivalent Thevenin's equivalent voltage is Thevenin's equivalent impedance. It is not like that because some boundary is there. Internally, if some kind of dependent variable is there, we are not supposed to transform some boundary. Okay, so though this session is very easy session, I'm supposed to take that. At the same time, boundary should be known. Boundary should be known. Okay. Anyway, before starting my class, let us share my details. I'm KN Rao, and 20 years of teaching experience plus in all very good institutes. Okay, and of course, I worked very longer period also. And subjects taken machines, network theory, and I may plan to take power systems also, depending upon availability and all. Okay, time. Anyway, if you want to keep me motivated, please like this session, share this session, and subscribe to our channel, Gate Conqueror. And see here, if you want to make me in your part, as part of your preparation, use my code KNR10. Yes. And in Unacademy, there are two kinds of paid platforms. One is Plus and another one is Iconic. In Plus, you are going to get live classes, crash courses, rank improvement batches, doubt solving sessions, and you can attend the classes in both English and Hindi. And if you think of Iconic subscription, which is actually a bigger one, like Superset, along with this, you are going to get personal coach also, who will guide you in your preparation, who will maintain the motivation in you in your preparation, and study planner. Because, for example, if I think of what do you say, working guys plan should be different compared to engineering studying guys or dedicatedly preparing guys. Okay, plan they are going to provide, and personalized test analysis, critical analysis, yeah, they are going to provide, and material also they are going to provide in Iconic subscription. Okay, and if you think of the fee structure for 12 months, if you use my code KNR10, it will become 27,225, and for 18 months, it is going to be 34,650, and for 2 years, it is going to be 39,600 for plus course. And if you think of for Iconic course for 1 year, it is going to be 40,500, and for 2 years, it is going to be 54,000. And no cost EMI facility is there. And they thought of increasing the fee structure from July 1st onwards, but they postponed that because of huge demand from the student community. At any point of time, very soon, they may increase the fee structure. And anyway, we don't have much time also. You have to take the decision, you have to start the preparation as soon as possible because gate is nearby. Yes. And Spark batch and Vero batch meant for only English speaking. Okay. Means all classes will be in English only. And in Spark batch is meant for gate 2022, and Vero batch is meant for gate 2023. And I'm going to start machines in this particular batch. And all the faculties I worked with previously, Vishnu Sir, Rajkanwal Sir, Suresh Sir, Trinad Reddy Sir, B.V. Reddy Sir, I worked with them. And Bhim Shankar is a very good faculty. And they're starting with signals and systems at 7 a.m. Okay. First class. Now this is Lakshya batch and Arohan batch. Classes will be in English or Hindi. And Lakshya batch is meant for Gator ESE 2022, and Arohan batch is meant for Gator ESE 2023. Again, all topmost faculties. Okay, R.G. Kanwal Sir, Varun Srivastav Sir, Ankit Goyal Sir, B.V. Reddy Sir, all. And yeah, this is about test series. Obviously, for paid course users, they have to provide test series, and they are providing test series. One thing, Unacademy is actually very big now. Okay, obviously, their content team should be strong now. Okay, you would get best possible test series. And follow me here at KN Rao for you, such that whenever I come to special class or live class, you will get the notifications and you can follow. Once you follow me, you will get the notifications. As per that, you can attend my classes and all. Next, let us start the session. Equivalent circuits. First of all, what is meant by equivalent circuit? Okay, boundaries are very important. Now, if I have one system, okay, for this system, let me consider terminal response characteristics. I repeat, terminal response characteristics. Okay, terminal response characteristics of this particular system terminal response characteristics. Okay, terminal response characteristics of first system should be exactly equal to the second system. Okay, this is altogether internally different system. This is system 2. This is system 2, and this is internally altogether it is different. This is system 1. But if at all, if both are maintaining same voltage current characteristics, okay, for example, it is giving at 10 volts, current is 2 amperes. At 10 volts, current should be 2 amperes only. Okay, maybe this might have been designed by BJT. This might have been designed by FET. Internally, they are altogether different. They can be altogether different. Okay, but external world only we are going to focus, because one thing, boundary is, just a minute. Yes, better. Okay, so boundary here, if you observe, for example, internally I have one resistance. Internally I have one resistance, and the current flowing through this resistance is Ix. And external means may not be inside the system. External to the system, I may have one dependent source, and that dependent source may be 3Ix. What is this? Current controlled voltage source. Okay. Now, if you convert this system equivalent with this particular system, meaning that this particular Ix is going to disappear, right? If Ix is disappeared, how can you solve this? No, not possible. Not possible. You're getting my point, right? So at any cost, if at all, if I have any control source beyond the system, in which controlling variable is inside the system, we are not supposed to transform at all. And next thing is, if they ask you anything internal to the system, for example, already I know how to transform sources. Okay, just let me take an example. For example, if I think of one voltage source in series with resistor, this is Vs, this is R. Okay, if I can convert this into equivalent current source, because boundaries are always very, very, very important. Okay, now this is going to be kind of Is value, and this is going to be same R value, and in between these two, if you see to the external world, they are going to maintain same terminal response characteristics, provided some link is there, we'll see later. Okay, now point here is, if they ask you how much is the power absorbed by this resistance, okay, because to the external world, both are same. But if you see internally, if they ask you, for example, forget about power, at least voltage, for example, voltage across this VR equal to how much? If they ask you, means can you transform this particular source from here to here, and can you expect that whatever will be the voltage here, same voltage will be there across this resistance, because this resistance magnitude and this resistance magnitude will be same, we will see later. But if they ask you voltage across this resistance, can I say that this particular voltage equal to this particular voltage? No. If something is being asked inside the system, you have to properly cross-check. Okay, kind of, see here, for example, if it is open circuited, okay, if it is open circuited, it is also open circuited. Then once it is this system, means external world, external system to be connected with this, if it is open circuited, under that condition, how much will be the voltage across this? Zero, because no current will flow. If you think of here, under open circuit condition, how much will be the voltage across this? Is into R is maximum. Getting my point, right? So if anything is asked inside the system, we are not supposed to go with equivalent circuits. Okay, because inside the system, voltage across this resistance and voltage across this resistance is altogether different. If you think of current flowing through the system, means under open circuit condition, how much current will flow? Under open circuit condition, how much current will go? Zero. Under open circuit condition, how much current will flow through this? Is going to be maximum under open circuit condition. So keep this particular point in mind. If anything is external to the system, when they ask you, then only you are supposed to go to equivalent circuits. Otherwise, we are not supposed to go. Let me take one more small example. Okay, means maybe from our 10th standard we know this, but let me extend this to boundaries. Okay, for example, this is resistance 1, resistance 2, resistance 3. Now, how much is the R equivalent across this? R equivalent across this is going to be directly we can write R1 plus R2 plus R3, right? R1 plus R2 plus R3. It is fine. It is fine. Perfect. Provided controlling variable is not there inside. For example, if I have one controlling variable here, that controlling variable is V2, and I'm going to have some other what they say dependent source on this particular voltage. For example, somewhere in the system, this is going to be maybe 2V2. This is voltage controlled current source. This is voltage controlled current source. Now, for example, if I convert if I convert this complete resistances into R1 plus R2 plus R3, where to keep V2? Without V2, how to calculate this? It is the matter of interest. Okay. So, means in this particular condition, what can be done? R1 and R3 can be combined, but R2 should not be combined. In the sense, in this particular condition, what I'm supposed to do? I'm supposed to keep R2 as it is, R1 plus R3, R2 as it is, R1 plus R3 combined, such that this particular V2 should have life. Because if it is having life, then only we can analyze this particular thing. Okay. Conclusion is very simple. If something is inside the system, if they ask you something inside the system, you have to check whether you can go with equivalent circuits or not. Otherwise, problem will come. Okay. Now, coming to the point, let us go back to equivalent circuits. Okay. So these are equivalent circuits, right? So when can we say these are equivalent circuits? Provided terminal response characteristics of this particular system and this particular system should be same. Under that condition, for example, terminal response characteristics of this particular system. Okay, this is voltage, this is current. If terminal response characteristic of this system is this, it is drooping. Now, this terminal response characteristics of this particular system also should be same to the external world. Then only means we can call it as equivalent circuit. Under that condition, we can replace this system 1 with system 2. Okay. Now, let us start with sources. Sources already we know, right? If two voltage sources are connected in series, it will be V1 plus V2 and all. But some conclusions are very important. Okay. See here, this is V1, V2. This is V1, V2. Equivalent is going to be V1 plus V2. You know, I know. Right? Just you have to apply KVL. Okay? If I apply KVL here, this is V. If I apply KVL in this direction, minus of V, I'm going to touch minus now first. Minus of V plus V1 plus V2 equal to 0. Such that V is going to be V1 plus V2. Same V should be there here. That is simple. Okay? Now, if I have series, it will be fine. And if I interchange the polarities, then it is going to be V1 minus V2. We need not bother about that much. Okay. But point to be considered here is, if I have one current source and one voltage source. Again, if something is being asked inside the system, we should be careful. Okay. Let me think of this as source current. Let me think of this as source voltage. Okay. What should be the equivalent for this? Because depending on this, we are going to derive one conclusion. And that should be kept in mind all the time. Okay. Now, see here. If I have this particular thing, what should be the output? Output should be IS only, right? It should be IS only. Because if I apply KCL here, means current is going to be IS only. What is current source? Current should be known independent of voltage. Now, current is known independent of voltage. So, this particular equivalent can be represented with this, provided some internal matter is not being asked. For example, if they ask you voltage across this, try to find voltage across the current source. Can you transform from here to here? No. Now it is going to be internal matter. This particular voltage will be different. This particular voltage would be different. Okay. Now, if they ask you, means the moment ISC is going to be same, voltages are going to be different, automatically power absorbed or power delivered by the source and by the source would be different. Okay. Now, what is the conclusion? Okay. Rather than source voltage, if I have anything, for example, this is some source current and this is some element. I need not bother about it. Okay, but except it should be current source. Means if it is also current source, problem will come. Conservation of charge is going to fail. Okay, except current source, whatever it may be here. Okay, whatever it may be here, it can be converted into current source only, equivalent. Okay, again, internal matter should not be asked. So what is the conclusion? You have to make note of it. Anything connected in series with ideal current source. Ideal. I'm not saying ideal independent or ideal dependent. For example, if I think of this is the situation. Okay, this is current source. Maybe 3ix. Ix dependent variable can be somewhere else. Okay, in this case also, equivalent is going to be, right, 3ix, because this is also ideal current source, Okay, means from starting only, if we can keep on include dependent sources in our analysis, our mind will be ready to accept that, and then it will be easy to solve later. Okay, after this session we are about to enter into problems and all. Okay, for problem, these are the basics which will be like which has to be there in the mind. Okay, now let me complete the statement. You have to write the statement, whatever it may be. See here, if ideal current source is connected in series with any other element except current source, then that particular equivalent is going to be current source only, such that whatever may be connected in series with ideal current source can be neglected, provided some information is being asked external to the world. I repeat my statement. Okay, anything connected in series with ideal current source can be neglected, provided if some information is being asked external to the system, not internal to the system. Because if some information is being asked internal to the system, obviously what you are supposed to do, you are supposed to consider this. Okay, for example, if I say this is Ix, okay, if I say this is Ix and Ix is linked here, now can I transform from here to here? Because if I transform from here to here, Ix is going to disappear. Once Ix disappear, how to solve this? Not possible. Okay, so means ideally, what is this actually? This is a current, right? Current is linked with KCL is linked with nodal analysis. Very soon it will come. Okay, conclusion is very simple. Anything connected in series with ideal current source can be neglected while applying KCL or while applying nodal analysis. Provided some information is being asked external to the system. Okay, now let us think of two current sources connected in series or two voltage sources connected in parallel. Okay, gradually we are entering into duality. Two current sources connected in series or two voltage sources connected in parallel. Then what will happen if this is V1, if this is V2, and if this is I1, and if this is I2? If I1 and I2 are different, not same, obviously KCL is going to fail here, right? Because I2 current is entering, I1 is coming out. I1 is coming out. How is it possible? It is possible only if and only if I1 equal to I2. For example, if I2 is 5 amperes, I1 is 10 amperes, I2 is giving 5 amperes, but I1 has to take, from the same node, I1 has to take 10 amperes. And the node does not have any of its own property. Okay, so it is possible only if equivalent circuit between this and this should be only current source. This current source magnitude should be I equal to I1 equal to I2. Okay, if I1 not equal to I2, what will happen? I'll tell you. Okay, and see here, if I move my charge, test charge from here to here, whatever may be the energy expended, if I take same test charge and if I move from here to here, same energy should be expended, because from here to here, these are all equipotential points. From here to here, these are all equipotential points. What does it mean? Means conservation of energy is going to fail if V1 is not equal to V2. V1 is not equal to V2. So what should be the equivalent? My equivalent is going to be V equal to V1 equal to V2. Now, if V1 not equal to V2, conservation of energy is going to fail, so we cannot analyze. At the same time, some people may think that if V1 is different and V2 is different, practically, if I take two batteries, 5-volt battery and 10-volt battery, if I connect them, what will happen? These are practical, no, they are not ideal. Okay, when practical, two different voltage sources are connected in parallel, what is going to happen? We will see once we start observing the practical sources. Okay, because these are all ideal sources. Ideal sources will be there on paper. Practical sources will be, practical systems will be there in the physical world. Okay, in the physical world, if you are able to connect two batteries in parallel of 5 volts and 10 volts, does not mean that you connected like this. Okay, there is some boundary. Anyway, now next thing is, if I connect one voltage source in parallel with current source or anything, parallel with current source, let me think of this as Vs, let me think of this as Is. Okay, then what is going to be equivalent? Obviously, we know, we need not explain that much. Okay, because for a current source, any voltage can be there, but for voltage source, voltage is given, this much voltage only should be there. So across this, how much will be the voltage with normal conditions? Means my Vs only should come here. My Vs only should come here. So equivalent is going to be Vs. Okay, now see here, if they ask you, for example, because my focus is boundaries, I have to repeat this multiple times such that you will not do this mistake in the examination. Okay, now for example, in your examination, if they ask you power absorbed by this or power delivered by this, whatever it may be. For example, power delivered by this is being asked. Now, if you convert this into equivalent circuit, can I say power delivered by this and power delivered by this will be same? No. Because if I think of this is open circuited and if I think of this is also open circuited, then what is going to happen? Under open circuit condition, how much will be the power delivered by this? 0. But under open circuit condition, how much is the power delivered by this? Power delivered by this is Vs into Is minus Vs into Is, because to the plus terminal it is going to enter the current. Actually, power is being absorbed, we can say. Okay, so power delivered by this under open circuit conditions is negative. Power delivered by this under open circuit conditions is 0. Meaning that we are not supposed to transform from here to here into equivalent circuits, provided if some internal matter is being asked. Anyway, see here. Now, not only current source, whatever may be the connection, see here, if I have ideal voltage source in parallel with anything, but this should not be one more ideal voltage source which is different, which is having different magnitude compared to this. Okay, if I have Vs here, then directly my equivalent circuit will be Vs only. Okay, what does it mean? Anything connected in parallel with ideal voltage source can be neglected, and that equivalent can be modeled with only voltage source, provided some information is being asked to the external world. Okay, anything connected, it means you have to make a note of this. Anything connected in parallel with ideal voltage source can be neglected in applying KVL. Because if you try to apply KVL, see here, if you try to apply KVL same. But if you try to apply KCL, it would be different. For example, how much is the current under open circuit conditions? How much is the current flowing through source? E is going to be Vs divided by Z. Vs divided by Z is going to be the current entering by the source. But under open circuit condition, current is different. Okay, logic is very simple. Let us combine these two statements. Okay, first statement is anything connected in series with ideal current source can be neglected while applying KCL or nodal analysis. Anything connected in parallel with ideal voltage source can be neglected. While applying KVL, because for a voltage source KVL application is going to be direct because voltage is known and KVL is depending on voltage rise or voltage drops only. And KCL meaning that what do you say, mesh analysis. KCL meaning that nodal analysis. Okay, KVL meaning that mesh analysis. Okay, anything connected in parallel with ideal voltage source can be neglected. Anything connected in series with ideal current source can be neglected, provided information is being asked to the external world. Okay, now let us think of source recombinations. Okay, source recombinations only done till now. Let us think of resistance recombinations. Okay, so in resistance recombinations, if I don't drag this discussion much because already you know, but I want to connect this to what do you say, duality. Okay, see here, voltage will be there, current will be there, same current is going to flow through all the elements, right? So what is meant by series? We have to, what do you say, define series, right? What is meant by series? Same magnitude of current should flow. I repeat, same magnitude of current. No, not same magnitude. I'm sorry. It is same magnitude. It is same current. Okay. Just a minute. I'll explain you. Okay. Same current should flow. Same current should flow through all the resistances or through all the elements. We can call it as series. Okay. So same current. What is meant by same magnitude also? I'll tell you just right now. Same current should flow through all the elements, then we can call them as series. Okay. For example, if I have, just wait, this is having 5 ohms and this is having 5 ohms, just like that. And if current entering is 2 amperes, then how much current will flow through this? 1 ampere. How much current will flow through this? 1 ampere. Now can I tell that same magnitudes of currents are flowing, so these two should be in series? Can I say that? No. Same magnitude, no. Same current. Okay, I hope you understood now. Like at starting I was confused. Okay, same current should flow, not same magnitudes of currents. Okay, now let us think of parallel. Parallel meaning that same node pair of nodes or 2 nodes. Okay, parallel means how many nodes are there here? If I think of this as node 1, if I think of this as node 2, all the elements are connected to the same node pair. Okay, so parallel means same node pair. Okay, same node pair is going to be parallel, same current is going to be series. Or from here, same node pair or same voltage should be there, no, everywhere. Okay, so for this resistance same voltage, for this resistance same voltage, for this resistance same voltage, or we can say same voltage, not same magnitude of voltage, but it is going to be same voltage. Same voltage if it is existing, that is going to be parallel. Or all these elements are connected to the same node pair of nodes, it is called as parallel. Now coming to here, in series same current should flow. Or at each and every node only 2 elements should be connected. Okay, so at each node only 2 elements. Right? Now in series same current should flow, or means at each and every node only 2 elements should be connected, because here also I'm going to connect one voltage source or current source, whatever it may be. Okay, now see here, in parallel same voltage should be there, or all elements should be connected to the same node pair. That's it. Now let us see. Now Yes. Okay. Now, already we know here the moment current is same. So here the moment current is same. What is going to happen? If I think of, I don't derive completely. It's not required, I know. Okay. If I think of this as R1, R2, R3, blah, 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 Rn. Okay. Now V1 plus V2 plus V3 plus Vn. Total voltage if I apply KVL equal to V. What is V1? I into R1. V2 I into R2. So if I take out I common, R equivalent of this is going to be R1 plus R2 plus R3 plus Rn. This is enough. Okay. If you think of parallel, okay, and in parallel, let me tell you one small thing. 1, 2, 3, 4. 5. Are they connected in series or parallel? We said series, right? Obviously, they should be connected in series. But let me change. Are they connected in series or parallel? Parallel now. Because one logic I'll tell you, simple. Whenever you have long short circuit paths, this is very important, keep that point in mind. Okay, you can make a note of it. Whenever you find long short circuit paths, give node numbers. I mean, this can be extended to machines also. Wherever you have long short circuit paths, give node number, then problem will become very simple. See here, if I think of this is node number 1, short circuit, this also will become node number 1. Short circuit, this also will become node number 1. Okay, now let me think of this as node number 2. This also will become node number 2. This also will become node number 2, or this will become node number 2. Now you should observe, this resistance is connected between 1 and 2. This resistance is also connected between 1 and 2, 1 and 2, 1 and 2, 1 and 2. What does it mean? All these resistances are connected in parallel, same node pair. Okay, you have to make a note of this. Whenever you have, because in our complete entire electrical engineering, in our machines, transformer, parallel operation also, like one toll gate question is there, just give node numbers, problem will be solved. Okay, so whenever you find long short circuit paths, give node numbers, problem is going to be solved. Okay, now okay, in this way it is going to be. Now what about here? Let me think of this is I1, I2, I3, In, and this is I. Now I equal I1 plus I2 plus I3 plus I4 and In. And now what is this I? V by R1. What is this I2? V by R2. What is this I3? V by R3. If you bring out V common, V into 1 by R1 plus 1 by R2 plus 1 by R3, so on 1 by Rn will come. Ultimately, it will become R equivalent equal to 1 by R1, R2, R3, Rn. 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by Rn. Inverse. Okay, V into 1 by R1 plus 1 by R2 will come. V by I is going to be R equivalent, so it will be reverse. Total whole inverse. Okay. Now, here again in parallel operation of transformer, we use this particular equation. Though it is simple equation, the moment it is machines, people are scared to use. That's it. Okay. In parallel operation, anyway, I'll tell that. See here, if I have only two resistances connected in parallel, multiple times we use this equation. Okay, everything is going to be same only, but multiple times we use this equation. So let me share that equation. Let us see current division rule here. And this particular equation we are going to use multiple times. That's why specifically I am going to tell this. Otherwise, it's actually simple one only. Okay. Now, if I have two resistances, because in parallel operation of transformers, parallel operation of alternators, multiple times we are going to use. Okay. Let me think of this as voltage. Let me think of this as current. Let me consider this as R1, R2, I2, I1. I am doing this not because it is complex. Okay, I am doing this because it is very much useful in that further level. So that's why I am going to derive a bit. Okay. Now, if you think of R equivalent is going to be how much? Two are connected in parallel. So this is going to be 1 by R1 plus 1 by R2 inverse. So this is going to be R1 R2 by R1 plus R2. Now same terminal response characteristic should be there. So the moment here I am having Vi, obviously same Vi I am supposed to have here. Now let me calculate voltage here. How much is voltage? Total current into R equivalent. So I into R1 R2 by R1 plus R2. Done. Now let me calculate I1 here. I1 here. How much is I1? V divided by R1. V divided by R1. How much is V? I into R1 R2 by R1 plus R2 divided by R1. R1 is going to get cancelled such that I into R2 by R1 plus R2 is going to be I1, has to be remembered. Okay, kind of, if I want to have current flowing through one of the resistor, total current into other resistance divided by total resistance. See here, I1 is going to be total current I into other resistance R2 divided by total resistance R1 plus R2. Okay, if I want to find current flowing through this is going to be useful if and only if two branches are there of parallel, not more than two. Okay, now current flowing through this is nothing but total current I into other resistance R1 divided by total resistance R1 plus R2. Okay, now let us think of inductors. Inductors I am going to explain because I am going to utilize duality concept in deciding about the capacitance. Okay, now inductors a bit I will write. A bit I am going to write, and after capacitance I am not going to write anything. Directly I am going to connect with the duality principle. Now let me think of series. Okay, in series, let me think of L1, L2, Ln, voltage, current, and equivalent is going to be L equivalent, same voltage, same current. Again, our basic fundamental rule is very simple. For example, if I think of voltage across this as V2, and if that V2 is controlling variable for any control sources outside, you are not supposed to merge this. Okay, except this you can include everything else, but L2 should be remained because depending variable, controlling variable is very much important for us. Okay, now see here, this is going to be, let me think of, see here, V1, V2, Vn. Now if I apply KVL, minus of V or V equal to plus V1 plus V2 plus Vn. What is V1? L1 into di by dt. Okay, so V is going to be V1 plus V2 plus V3 and all. So I, L1. What is V1? L1 di by dt. So L1 di by dt plus L2 same di by dt. Now if I take common di by dt, it is going to be L1 plus L2 plus L3 plus di by dt. Now same equation if I write for this particular voltage. Okay, so what is V here? V is going to be L equivalent into di by dt. That's it. So what is L equivalent is going to be this. Okay, so for series connection, it is kind of resistance only. For resistance series, R1 plus R2 plus R3 like that. For inductance series, L1 plus L2 like that. I am not going to derive anything more. Plus Ln. Done. If you think of parallel, okay, so if I think of inductors parallel, same kind of resistance equation only should come. Right? Now, if I think of inductors parallel, then how much is L equivalent? L equivalent is going to be, if I see from here, is going to be 1 by L1 plus 1 by L2 plus whole inverse. Okay. Immediately after this, we will be able to solve problems. Okay. Now, let me think of capacitance. Now, between capacitance and inductance, what do we know? In capacitance or capacitor, whatever it may be, ideal capacitor, in between inductance and capacitance, what do we know? Inductance, current, capacitance, voltage. Duality, already we developed this, right? And capacitance current is nothing but inductance voltage. Okay, meaning that, see here, in series, current is going to be constant. Current is going to be same. Current is going to be same. And in parallel, voltage is going to be same. And between inductance and capacitance, current will become voltage, voltage will become current by duality, we know. So, if I think of series connection, I have to use kind of equation of parallel. Okay, parallel resistance or parallel inductance kind of stuff. This is C1, C2. Let me calculate C equivalent across this. Now, if I calculate C equivalent is going to be, this is series. Kind of parallel equation of inductance or resistance has to be used. So, 1 by C1 plus 1 by C2 plus 1 by Cn inverse. Okay. If I think of parallel, okay, for parallel connection, series kind of resistance or series kind of inductance formula has to be used. That's it. Because between inductor and capacitor, voltage is becoming current, current is becoming voltage. Okay. If I have this as C1, C2, and if I want C equivalent is going to be, this is enough. This is enough. From next session onwards, we are going to solve problems. And from this point onwards, we are going to enter into solving problems. Immediately, we are going to take KCL, KVL. Mesh nodal analysis. In mesh nodal also, directly we are going to take problems only. From now onwards, multiple problems we are going to solve. Okay. And like the session, subscribe to the channel. Thank you.